Hello, good evening, students. In last lecture, we have discussed about the strain energy. Now, today's topic is strain energy in pure shearing. In last lecture, we had discussed about the strain energy due to the gradually increasing load, suddenly applied load, and impact load. Now, strain energy in pure shearing. Consider a rectangular block or rectangular block of material subjected to shearing forces S acting across two of its opposite faces. The face LM will move relative to face NP a distance mm dash is equal to the mn into phi, where phi is the angle of shear produced. Okay, this is phi. Now, the work done is equal to the 1 by 2 S into mm dash or 1 by 2 into S into mn into phi. Here mm dash upon mn is equal to 10 phi or equal to phi because phi is very small. Okay. Now S is equal to tau into Ln, where tau is the shearing stress and phi is equal to tau upon C. Phi is equal to Es, which is known as shear strain. Taking unit depth normal to diagram, strain energy will be equal to the work done. Here strain energy is equal to the tau square upon 2C Lm into Mn. Now Lm into Mn is the volume of rectangular block. Since it has unit depth normal to LMNP, since strain energy U will be equal to the tau square 2C into volume of block. Okay, this will be the strain energy due to the shear stress. Now किससे लाइट लो आराम कर लो ना, क्या बुखार आ रहा है? Now, strain energy in torsion. Consider a solid circular shaft of length L and radius R. Consider a solid circular shaft of length L and radius R subjected to a torque T producing a twist theta in the length of shaft. Okay. Now the work done work done is equal to 1 by 2 T into theta, but T upon IP is equal to C into theta upon L is equal to tau by R, where T is the torque applied on the shaft, where T is torque applied, Ip is equal to the polar moment of inertia, C is equal to the modulus of rigidity, L is equal to the length of the shaft, length of the shaft, tau is equal to the maximum shear stress on the surface of shaft. Now T will be equal to the tau into Ip upon R, and theta will be equal to the tau L upon Cr. So the work done will be is equal to the 1 by 2 tau into Ip upon R into tau into L upon Cr equal to 1 by 2 tie square C Ip into L upon R square. We know that Ip is equal to polar moment of inertia is equal to pi r square by 2. Ip is equal to pi r square by 2. Now putting this value in the above equation, then work done is equal to the okay, this will be the work done. Now strain energy U will be equal to the tau square force into volume, because pi r square L is equal to the volume of the shaft. Okay. Now strain energy due to the bending. Let us consider a beam consider a beam of uniform cross section with certain end conditions, such that the bending moment varies along its length. Consider a small length dx of a beam where the bending moment capital M. Consider further a small strip EFGH of thickness dy at a distance y from the neutral axis. Okay, let B be the width of strip. Volume of strip is dx into dy into B. Okay. Now, since strain energy of a small volume dx dy into b will be equal to the stress on EFGH to the power 2 divided by 2 into E into volume. Okay. Within C dash D dash D. Integration m square dx okay. Now now moment of inertia of beam cross section is equal to I. Now du will be equal to the now integrate the equation. Now total strain energy will be equal to the m square L upon 2 EI. Okay. Now come to the next topic, strain energy due to principal stresses oblique strain energy in general case. Okay, any compound stress condition can always be reduced to the condition of three principal stresses. Thus, general strain energy equation reduced in terms of three principal stresses can be useful for all the compound loading on a body. So, let a triaxial system system sigma 1, sigma 2, sigma 3 as the principal stresses be acting on a small block of length delta L delta B and height delta H. Strain in respective three directions. Where mu is the Poisson's ratio and E is the Young's modulus. Let the extensions in three directions are x1 is equal to E1 into delta L, x2 is equal to E2 into delta B, and x3 is equal to E3 into delta H. Strain energy due to sigma 1 is equal to the 1 by 2 load due to sigma 1 in the direction of sigma 1, which is sigma 1 into delta B into delta H into delta L upon E okay, it will be equal to 1 by 2 E So the total strain energy due to the sigma 1 will be equal to this. Similarly, strain energy due to sigma 2 is equal to 1 by 2 E sigma 2 square minus mu sigma 2 sigma 1 plus sigma 2 sigma 3 delta V, and strain energy due to sigma 3 will be equal to the 1 by 2 E sigma 3 square minus mu sigma 3 sigma 1 plus sigma 3 sigma 2 delta V. Total strain energy will be equal to the okay. So total strain energy U is equal to the 1 by 2E. Okay, this will be the total strain energy. U is equal to 1 by 2E sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 sigma 1 into वॉल्यूम. एक बार फिर से इसको देख लेते हैं. First of all, consider we had considered the rectangular block whose length is delta L, width is delta B, and height is the delta H. Three normal stresses are acting on in the x, y, and z direction: sigma 1, sigma 2, and sigma 3. These are the principal stresses. No shear stresses are acting on those planes, these planes. Okay. Now, from the generalized Hooke's law, we know that the principal strain in the direction of the stresses. So the strain in the direction of sigma 1 will be equal to the 1 by E sigma 1 minus mu sigma 2 plus sigma 3. E2 will be is equal to the 1 by E 1 by E sigma 2 plus sigma minus mu sigma 1 plus sigma 3. E3 will be is equal to the 1 by E sigma 3 minus mu sigma 1 plus sigma 2. Minus mu is equal to the Poisson's mu is equal to the Poisson's ratio, and E is equal to the Young's modulus. Now the extension in the three directions are x1 is equal to the strain into total length delta L, x2 is equal to E2 into delta B, x3 is equal to E3 into delta H. The strain due to the sigma 1 will be equal to the 1 by 2 sigma 1 into delta B into delta H into extension, which is x1, 1 by 2 sorry 1 by 2 E sigma 1 square minus mu sigma 1 plus sigma 2 sigma 2 plus sigma 1 sigma 3 into delta L into delta B into delta H. Now from here sigma 1 is equal to the 1 by 2E. Strain energy due to the stress sigma 1 equals to the 1 by 2E sigma 1 square minus mu sigma 1 sigma 2 plus sigma 1 sigma 3 into delta V. Similarly, we can determine the strain energy due to the stress sigma 2 and sigma 3. Now the total strain energy will be equal to the sum of strain energy due to the stress sigma 1, sigma 2 and sigma 3. So delta U will be equal to the 1 by 2E sigma 1 square minus mu sigma 1 sigma 2 sigma 3 sigma 1 delta V 1 by 2E sigma 2 square minus mu sigma 2 sigma 3 plus sigma 1 sigma 2 into delta V plus 1 by 2E sigma 3 square minus mu sigma 3 sigma 1 sigma 2 sigma 3 into delta V. Now 1 by 2 is count from the equation. We have sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 times 2 mu sigma 1 sigma 2 sigma 2 sigma 3 sigma 3 sigma 1 into delta V. So the total strain energy will be calculated by integrate this equation. So by integrating this equation, U is equal to the 1 by 2E sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 into volume. This will be the total strain energy, and strain energy per unit volume will be equal to the 1 by 2E sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. This will be the total strain energy due to the principal stresses. Thank you very much.